So I'm going to say a few things about how to make constraint satisfaction more efficient. We're going to be looking at three different methods. One of them is called forward checking. The other one is called arc consistency or constraint satisfaction. There we're going to look at the AC3 algorithm. And we're going to look at some more involved means of doing inference. All of them can be considered as doing inference. And some of them are very close to, or some of them incorporate some of the methods that we use when we play Sudoku. So the simplest form of inference is called forward checking. So what we're going to do is whenever we make a choice, whenever we assign a value to a variable, we can look at all the variables that are connected to this first variable by the constraints and eliminate certain possibilities, certain values in the domain of the connected variables. So that's what we're going to do in forward checking. So in forward checking, we're only going to look at the variables that are immediately connected to the current variable. So since Sudoku is kind of a pretty big problem, what we're going to do is we're going to look at a smaller one. We're going to look at a smaller example. We're going to have four variables, x, y, z, and t. Each of these variables has the same domain, 1 to 3, and here are some of the constraints. So what I'm going to do is I'm going to draw this as a constraint graph. So x less than y, x less than t, t less than z, y equal to z. But before we look into forward checking, it would be helpful to understand how this is going to be done in backtracking, so we develop a better understanding about the improvements of forward checking as well as constraint propagation. So again, let's use plain old backtracking, and we're going to solve them in the order of x, y, z, and t. So we're just going to go around in a clockwise fashion. So in backtracking, we'll start with x, and we'll pick 1. Great. So then we move y. We can't pick 1 over here because it violates this constraint, so we'll pick 2. Then we move on to z. Again, 1 violates this equality constraint, so we pick 2. Then we go to t, and so 1 satisfies this constraint, but it doesn't satisfy this constraint, so we'll have to pick 2, but 2 satisfies this constraint but violates this constraint, and 3 also violates this constraint, so we have to do backtracking. This one didn't work. We run out of values for t. So we go back over here and we undo the assignment to 2, and we now pick 3. Okay, but 3 violates this constraint. So we run out of options over here, so we actually have to backtrack all the way to y. Okay, and so here we're going to undo the 2 and we're going to pick 3. Like that. So now I go forward. Again, when I go forward, I'll start again at the bottom. There's no memory of what may or may not be evaluated. So 1 doesn't satisfy it, 2 doesn't satisfy it, so we pick 3. So 3 is now assigned to z, and then we'll move forward to t. And so we'll start with 1 that violates this constraint. So we'll pick 2, which satisfies this and that constraint. And there you have it. We have a solution using backtracking. All right, so very good. Well, let's see then what forward checking will do for us. So in forward checking, when we make an assignment, we will look at the neighboring variables, the ones that are connected to ours by constraints, and eliminate values from the domain, even before we consider any of those variables. So when I assign 1 to x as a tentative value, I can eliminate 1 from this domain and 1 from this domain, because obviously they would violate these constraints. So then I move on to y, and I pick 2. So now, based on this choice, I can now eliminate 3 and 2 from this domain, because obviously they wouldn't satisfy the less than constraint. And I can eliminate 1 and 3 from this domain, because it wouldn't satisfy the equality constraint. So that's what we're going to do. Then we're going to move down here. We're going to pick 2 for z. And then based on that, I can eliminate this one here, because that obviously wouldn't be equal. And then I'll go on and eliminate 3 and 2 from this one over here, because they wouldn't satisfy the constraint that t is less than z. Okay, so now we run out of options for t, so we have to backtrack. So we go over here. I have to pick a different value for 2. And so again, as you can sort of like guess, we're going to run out of options. Now I should tell you that when we backtrack, we're sort of like going to undo some of the constraints that we enforced. So I'm going to make 2 and 3 black again because I enforced them or I propagated them when I made this choice. So then when I undo the 2, I can also undo this one over here, the 3, because I enforced that thing when I made the choice of 2. Nevertheless, we have to also backtrack back to y. But what I want to tell you is that this one here will now be black. Like so. And when I change the value from 2 to 3, I will also update this constraint. So I'll undo whatever I did and then redo what I need to do. So the 2 now is black. That's the upshot of it. 3 obviously can't be is not a viable value because it doesn't satisfy this constraint. So I pick 3. Again, this one is still there from the original assignment to x. And I'm going to enforce this constraint, which means I eliminate 1 and 2 from this domain. So then I move down here, I'll pick 3. And again, there's nothing to remain to enforce over here, but obviously I will eliminate 3 over here. So now I'm going to go to t, I'm going to pick 2, and that satisfies this constraint, and so I have found a solution through forward checking. So a little bit different of an algorithm in the sense that even before we visit a variable to make a choice, we sort of like modify its domain a little bit. All right, so, but maybe not too much of an improvement. So let's have a look at constraint propagation. What we're going to do over here is, rather than forward checking where we only look at the immediate neighbors, we're going to sort of like look at the transitive closure of all neighbors, and we sort of like propagate constraints until no more constraints can be propagated. And this is kind of like what we do when we play Sudoku, because very rarely do you ever sort of like say, okay, well, I am stuck, I gotta make a choice, because you know it's not going to work out, right? Many times. Sometimes it does. So let's have a look at this thing. So in our consistency, before we make any choices, we're going to look at the domains and we're going to enforce certain constraints. So again, no choice for x at this point in time, but let's look at this thing, right? We can eliminate, let's see, y from this domain because 1 can never be larger than this one over here, right? Same thing over here, we're going to eliminate 1 from this domain because it can never be larger than that one. And so conversely, we can eliminate 3 from this one because it can never be less than 3 or this 3. So 3 goes away over here, 1 goes away over here, 1 goes away over here. So that's what we have. So we have 3, 1, 1. Now, let's see what else we can eliminate. So we can eliminate this 3 over here because for similar reasons of these inequalities, because it can never be less than this 3 over here. So 3 is gone. We can eliminate this 2 over here because it can never be larger than this 2 over here. So that got eliminated over here. And same thing for the 1, obviously can never be larger than this 2. Now notice that we eliminated this 3 earlier, and so based on that, we are only left with 2, and we can now eliminate this 2 over here because this 2 can never be less than this 2 over here. So now we explain these two, and that one, and so this 2 over here gets eliminated because of this equality constraint, right? So we're only left with this one. And now, without ever picking anything, just sort of like enforcing constraints over and over again, we actually have found a solution, the only viable solution, right? So now we would pick 1 for x, 3 for y, 3 for z, and 2 for t. So that's what we're going to do. So the most popular algorithm for this thing is AC3. And I don't want to go into the details of it. I have some slides over here. I encourage you that based on what we just explained, have a look at it. And if you have any questions, just talk to me. What I want to do instead is I want to sort of talk a little bit more about how one might solve this thing on the computer then. So typically what we do is we interleave constraint propagation and backtracking search. So what we would do is we would do constraint propagation until no values change anymore. If it's solved, great, we're done. If not, we save the state to the stack. Then we pick a variable and a value and assign it to it. So from any of the variables that have more than one choice, we pick one. And again, there are strategies for doing this. And then we make a recursive call to solve. And again, if it's success, we return. If not, we have to restore the old state and then pick the next value. And again, there are many different strategies that you can pick. I don't want to spend too much time in this course on constraint propagation. I just want to do it so that you can implement Sudoku and sort of like develop an understanding of what it might be to do AI. So let me finish off by saying a few things about some more heavy-duty inference. So let's have a look at this column over here with these values. And let's focus on this one, this cell over here and this cell over here. So notice that we have a 1 and a 6 over here and a 1 and a 6 over here. Since these are only pairs, what we know is that in this column here, the 6 either has to be in this cell or in this cell, and the 1 in this one and this one also. It doesn't matter if the 6 is in here, or vice versa. But what that means is that we know the 6 can't be in here, okay, because it's got to be in one of these two cells, and it can't be in here either or in here. So we can eliminate 6 from this domain, and from this domain. Similarly for 1, the 1 has to be in here or in here, so we can eliminate 1 from this domain and 1 from this domain. That's what we have over here. So we eliminate 6, 1, 6, 6, 1 from this one over here. All right, just by sort of like thinking about this thing. And again, so this gets to a point where it gets to be harder and harder to capture that through constraints and constraint propagation. So this is some sort of like pretty heavy-duty inference that we're going to be doing. Let's have a look at this one over here. Turns out we can do a few additional eliminations. Let's have a look at let's see, this cell over here, this cell over here, this cell over here, and this cell over here. So we have the value 3, 4, again 6 is gone, 4, 7, 3, 4, 7, and 3, 4. Okay. So again, the second cell and the bottom two cells. That's what we're going to look at. Now we know that that the 3 and the 4, either the 3 and the 4 has to be in here, and either the 4 or the 7 has to be in here. And this one over here also, 3, 4, 7, right? So those are our choices. Now again, theoretically speaking, the 3 and the 4 can be over here, but we want to look at those 3 values that we have, right? So it turns out that based on the fact that this one has to be 3, 4, 7, this one has to be 3, 4, and this one has to be 3, 4, 7, we can eliminate 3 and 4 from the top cell. Because again, they cannot be there. We only have 3 values, and they need to go here, here, or here. And what that means is we're going to be left with just the value 8 over here. So that's pretty cool stuff. Alrighty, folks, that's it. I'll talk to you later. Bye.